Welcome to Frontline Systems special webinar on best practices for scheduling optimization applications using Analytic Solver. This webinar is an outreach from our dedicated customer success and support teams to make sure you are getting the most out of our products. During this webinar, we walk through the key concepts and strategies for modeling the scheduling and production optimization applications using Analytic Solver. We are going to start with a step-by-step modeling of a workforce scheduling application. This is a two-step or two-stage model. And then we go over using VBA to define and automate the two-step workforce model optimization. This aims to familiarize you with the art of automating your Excel spreadsheet optimization models if you want to have your own custom applications in Excel. However, remember in previous webinars, we discussed that Analytic Solver and Rayson offer you much more and allows you to go beyond Excel when you want to create your custom applications. There's much more you can do. After that, we will review another allocation and production modeling application in the agricultural industry with uncertainty, and we will use recourse decision variables and use the power of stochastic optimization to make the best decisions. So what is a scheduling optimization? Generally, the optimization goal is to efficiently allocate scarce resources, allocating right number of resources to right places at the right time. When it comes to scheduling optimization, you are constructing a schedule that will be as efficient as possible. And depending on industry, and scheduling may refer to transportation planning and routing, product planning, workforce planning, project workflow planning, and much more. Job shop models, and there are more. There are different factors that you may want to consider for modeling your scheduling or planning problems. This is just a summary. There are, of course, more details, but what are your available or scarce resources? This is very important. This can be your staff, equipment, vehicle, raw material, assembly lines, time, budget, and so on. Demand or amount of work that's required. So how much demand that needs to be fulfilled, number of goods manufactured, amount of services provided. So you need to know all of this before modeling, before starting your modeling. Other monetary consideration or expenses, costs or operating costs or capital expenditures that impact the financial results, such as payroll, overtime compensation, mileage costs, depreciations, storage costs, and so on. When it comes to the optimization and the components of an optimization model, you need to come up with these three parts of the optimization. Determine your decision variables, and you can ask these questions. What are the factors that are under our control? You need to determine your objective function. This is the measure you want to optimize. So ask this question: what is the measure that's most important for me to optimize? And it can be the goal you want to achieve, maximize your profit, number of items produced, minimize costs, risks, and you want to optimize the preferences of people, and much more. We also have hard constraints. These are restrictions that limit your choice of decision variables and cannot be changed and must be considered. So for example, number of working and overtime hours per week, government regulation, physical constraints, capacity restrictions, how much a warehouse can hold, number of patient a nurse can visit, or amount of time to travel between different appointments. So these are like hard constraints. They must be satisfied, and they define your feasible region for your optimization model. There could also be some soft constraints, the ones that are desirable, but they are not mandatory. For example, individual employee preferences. Okay, so this could be part of your objective. You try to maximize it, but it is not a hard constraint. The preference of people, work, which shift they want to work on, or customer priorities, and much more. Okay, and then also you could have key performance indicators and measurements that show the effectiveness of your schedule and how you can compare them to support your decision making. Okay, so this was part of the factors to consider. Okay, so let's start and look at our first example. A call center requires a certain number of employees each day of the week to operate. Every employee must be on a schedule that allows him or her 2 consecutive days off. How many employees should the call center hire, and how should the schedules be set for each employee to minimize the total payroll cost? So what are inputs to the model? You can see we have the different schedules, A, B, C, D, E, F, G, the 2 consecutive days off. And the goal here is just to hire number of required people. And you can see we know that on Sunday we need 22, on Monday we need 17, and so forth. So the daily pay rate is 40. So here are the decision variables. I'm pretty sure most of you are familiar with how to define an optimization problem, so I'm not going to spend a lot of time on that unless someone requests. Variables are employee per schedule. So this is this block defined. You remember you can work with name ranges in Excel. So here are employee per schedule. And again, we are dealing with number of people. So we have some constraint on variables. You can see under bound. Let me highlight here that we have employee per schedule should be positive. So we want to get everybody assigned a positive value, number of people, and then also integer, right? We want to make sure we're whole numbers, working with whole numbers. And what constraints we have? Employee per day should be greater than required employee. This is the constraint. This is the what the need we have. And our objective function obviously is to minimize total payroll cost. And let me show you the calculation. Let's see, pay rate here and objective is here. So it's just the calculation of, we calculate total number of employees in cell D20 and then multiply it by daily pay rate. Very straightforward model, right? Okay, so let's go ahead and optimize this and get the results. So I click on optimize. We walk through guided mode. This is a straightforward LPMIP, linear programming, mixed integer programming. The reason is we have those mixed integer variables that are employee per schedule. Click on next step and we get the results. Solver found the optimal solution. So here are the number of people that we need to hire, okay? We are going to copy this part and use it for the next part of our model, the stage 2. So we hired 25 people. We know how we need them. Like now we need total of 3 people for schedule A and 5 people for schedule B with this kind of a schedule, like consecutive days off. And we come back here. But now we have to assign people to this schedule. So I just want to make sure this part is clear. So I copied the results of a first model down here. Number of employee per schedule. Now we move the schedule A, B, C, all the way to G up here. Okay, is that clear? So after the call center hired the necessary employees, they need to schedule them. And to make this a fair process, they ask each employee to rank each schedule based on their preferences. So remember, 2 consecutive days of schedule A was, we have it up here too. Schedule A is Sunday, Monday off, B is Monday, Tuesday, and then G is probably the most preferred is Saturday, Sunday off. Okay, so we asked everyone, all of those 25 people that we hired, to give us their preferences. And this is the preference table. So it's an input to the problem. So here is employee number 1. Now, with all the employee preferences that are captured, how should the park schedule the employees to attain the greatest employee satisfaction? Okay, so this is a very important way of looking at optimization problem. This is a scheduling application, but it can be used in assignment type, different type of assignment, and routing problems, especially when you're dealing with decisions that are yes, no. So we are using binary decision variables because for each employee, we have to decide, is she going to be assigned to schedule A or not? Okay, so we are going to use binary decision variables, and we have this large binary matrix. Okay. And again, remember that we have solved the first stage. We copied the results. Variables are scheduled to which employee assigned. You can see this whole block is defined as a schedule. These are our decision variables. I also define them as binary and of course non-negative. We all know that there is an option to set assume non-negative to true, and this is under engine. Assume non-negative, you can change this to true and make sure that all the schedule get positive values. Here, when you say binary, of course, it's obvious we are going to get 0 and 1, right? So if you don't set that, it's also fine. Now, what are the constraints? When you have a large binary matrix, it's actually really easy to calculate everything. One of the constraints, employee schedule must be greater than or equal to employee required, the demand. So we have simple sum functions under each column, easy to manage. And then we have this constraint, employee schedule. This whole block should be greater than employee required. Schedule per employee should be equal to must be equal to 1. This ensures that each employee receives one and only one schedule. How do we do this? We just calculate in each row the total number of assigned schedule per employee, and then we make sure we force that to be 1. So each employee can only be assigned to one schedule. And let's calculate the preference of each schedule for each employee. So we just use sum product, multiply everything together, and then add all of these preferences in cell U55. This is total preference, or our objective to be maximize total preferences, okay, in cell U55. Let's click on optimize, continue, next step, LPMIP, and here are the results. And you can see we have employee number 1 is assigned to schedule number B. Employee number 2 is assigned to C, and you can see the preferences are 5 and 6 and 7. So, okay, there are a few 4s, but that's how you can maximize the preferences. It is not a hard constraint. We consider an objective, and here are the results. But remember, it was a 2-stage optimization. Okay, you had to solve the first stage and then solve the second stage. So in the first stage, we determined the optimal number of employee per schedule. In the second stage, we added the employee preferences into account, and the other one was the seniority. Instead of running one optimization model and then running the other one, we can run the two models automatically using VBA. So this is a good time to talk about VBA, okay? And then we will come back, and I'm going to show you step by step how you can run a solver model. We're going to write the code together using VBA, and then we look at the advanced use of VBA. Here we have a macro that actually defines the whole optimizations from scratch, because if you look, there is no optimization defined. So we are going to define the optimizations from scratch and then automate the 2-step of the optimization. Automating your models using VBA for Excel users have been supported for our products for many years. Automating your models allows you to run your predefined solver models and control the solver. You can automatically update data, run the model, and retrieve the results. VBA can also help you if you want to run multi-period optimizations when the output of current model is the input to the next model. Another important application is to create an application or dashboard to distribute to your end users, okay? However, when it comes to creating applications from your models, you have many other choices. So let's go back to Excel for a second. Remember the deploy model options. This is with the power of Analytic Solver and Raison Server, and you can do much more. You can embed your model into your own application, solve it on the web, within Power BI, within Tableau, with calling our Raison Server. You can create a web application, your own SDK application, and with a few clicks, you can create a web application, and you can actually host your Excel workbook results in Microsoft Teams, okay? So there are all these deploy options available to you that can be used wherever to enable your model to be used wherever and whenever it is needed, on the factory floor, salesperson laptop or smartphone, or in a call center custom application. I have covered these topics in the previous webinars. If you're interested, we can share a recording with you, and they're all available in Frontline Solver's YouTube channel. But I just wanted to mention to you, there's a lot of options you have when you want to create an application, but still using VBA and creating custom application in Excel is a trend, and I just wanted to cover that briefly for you. So let's go back here. So you can create, modify, solve optimization under control of your custom application in VBA. Analytic Solver supports both object-oriented VBA and traditional VBA. Highly recommended to use the object-oriented API because it's more powerful and more convenient. You can work with objects that correspond to problem models, solver engine, variables, and functions. And also it allows you to access set of variables, constraint in kind model directly with expressions that we will talk about, like my prop.var decision or my prop.function constraint, okay? And then the result in VBA code easier to read and easier to write. You will receive IntelliSense prompts as you write each code, which make it much easier to work to write code and without consulting the manual. Also, you can use object-oriented API when programming with languages such as VB.NET, C#, C++, working Visual Studio, and you will still receive the IntelliSense prompts in the syntax of those languages as well. If you have worked with Solver SDK, you know that you can work with Python, C++, C#, and much more, okay? If you are planning to move your application outside of Excel in future, you want to have a standalone program, and you find that Solver SDK offer object-oriented API that closely resembles the API in Analytic Solver, okay? I'm going to show you now how to call the solver from VBA and retrieve one of the reports, okay? Something very simple. Let's go back to our Excel model. Okay, the first stage, okay? Let's just work on this one. Analytic Solver. I'm going to use a shape, circle shape. Now, let's assign a macro to it. So right click, and you can see there's the assign macro. This is, of course, one of the many ways you can do this. So all one click, it's a new macro, and it opens the Visual Studio for you. Okay. Just before starting, let's click on Tools, References, and make sure you have a reference to Analytic Solver 2023 type library. Okay, so you get all the maximum recent engines, you get that object-oriented API, and also get all those IntelliSense prompts. Okay, so that's checked. Okay, here, first step is to define an instance of a problem. Okay, and by default it's associated with the active worksheet. Okay, we have one worksheet here, so it's easy. So to do that, you can type in dim problem as new, and you can see the IntelliSense prompt, right? Tab as new, and then if I put problem, I can use tab, and then it inserts it for me. Okay, dim prob as new problem. So I define a new instance of problem. And if you want to optimize, you can easily just say, this is the next line you need, prob dot solver tab dot optimize. Okay, this is all you need to run the optimization. Now, if you want to retrieve one of the reports, let me show you how you can do that. So you can basically type in prob dot solver dot report, and then comma and the name of report you want to get. Answer report. Okay, I'm going to show you how to get answer, and this is how you're going to automate the optimization and get an answer report at the end. Okay, so let's save this. I'm going to close this one. Let's look at the output. It's empty, and let's click on our button. Okay, so as soon as I click on the button, it brings me guided mode. You can, of course, turn off the guided mode automatically using VBA code or also in the setting, but let's click on continue, next step, and we get the results. Okay, and as soon as I click OK, here's our answer report. Okay, let's click on answer report, and it's generated for us. Any questions so far? And I'm going to show you more advanced VBA model in the other model, the two-step optimization. So up to this point, we solved the model as it has been previously defined interactively in the worksheet. And now we are going to move forward with a more advanced application. We are going to start with a worksheet that has only some Excel formulas no solver model defined. Okay, to save time, it's all created, so we don't need to spend a lot of time here, but I will show you the code. Let's go back to our example. Okay, you can right click and then actually go to edit, or you can just go to developer, okay, and then go to Visual Basic. So we want to define the two optimizations, the stage 1 and also stage 2, and then run them after each other and get the results. Okay, so first step, of course, they can sub run solver, that's the button, and then the macro, and then end sub. Okay, it ends here at the end of running both defining and running both optimizations. So first step, initializing new problem with defining the with using dim prob as new problem. If you have multiple worksheets, here the code show you how you can actually use the active worksheet, define the active worksheet. So here is the scheduling plus seniority. Remember the third tab, okay? Now, since we are going to define first optimization, run it, use the results for the second optimization all together, we have to clear the first remember, in each workbook you can have only one optimization, right? But here we are going to define two optimizations. So we have this line of code, the clear worksheet of previous models. Okay, so basically clears the variables, clears the functions, and all the engine parameter settings. Okay, now this is how you define decision variables and define them as integer. So dim variables as new group of variables, and then you pass the variable type, okay, and variable row bound, variable integer type, okay, and then add the variables, prop.variables, add variables. Okay, so you have to add the variables separately, and then you can add your constraints similarly. Remember, the stage 1 employee stage 1 model employee schedule should be greater than employee required, so you add the function. So this is a very good example to show you how you can add constraints. Okay, so this is where at the end add the block of constraint. Define the constraint. You have to define this the function type constraint, and then lower bound, because it's the lower bound is stage 1 employee required, and you can see we are passing the numbers. Okay, next, the objective. So we added the inequality constraint to the model. We defined the objective, define a new instance of an objective. What is the function type? This time function type objective, okay? And add the objective to the model. And the problem type, which is minimization, okay? So in these two lines, we add the objective and also we define the solver type minimization. So now you can optimize the model using engine that's automatically selected by solver, or you can actually pass the engine with a one line of code, okay? And then if you want, it's just a loop here that displays the final results for you, okay? Prop.solver optimize, we run the optimization, we display that optimization results are basically, we display a status 1, meaning model is fully optimized, and here are final results. So once that's done, we're going to clear the task pane because optimization will be added. We're going to clear the task pane with clear worksheet of previous models, and then define the second stage of the optimization. So defining variables, constraints, okay, all the constraints are added. Remember, we had two sets of constraints, a set of equality constraints. So this example show you how to add equality constraints from scratch, and then remember, the stage 2 schedule period was equal 1. We wanted to make sure each employee is only assigned to one schedule. So this is how you add that to the model. Okay, so basically you have a lower bound and upper bound of 1. Okay, and then add the objective, just like the other one. This time we are maximizing the employee preferences, so solver type maximize for the optimization. Same way, prop.solver optimize, and then we get the result messages. Finish the function and clear everything. Okay, so let's close this. Come back here and run the solver. Run the macro. So this is the first status. Remember that if function, we are getting a status, solver found the solution. This is the message we wanted to display. Now we are going to solve the second stage of the model. And again, solve for an optimal solution. And we're done. Let's see the results. You can see all the results are here. And remember, we had the seniority in this model. So we solved the first stage, cleared the model, because if you go back to the model, we deleted everything, right? So there's nothing defined in task pane. And then we defined the second part, used the results from the first part, and then got the result. I hope this was helpful to give you an idea how you can work with VBA. Let's move on to our second part of the webinar. If you are interested, I have summarized all these details for you in these slides, automating how to automate a predefined optimization model in VBA, and then summary of how to actually create a solver model from scratch. Now we go into our next application in the agriculture industry. If you go to Analytic Solver, click on Help, and then click on Example Models, you can see we have a group of optimization as the examples. These are deterministic optimization examples. Just like the scheduling model, there is no source of uncertainty in these models. And then we have stochastic optimization examples and simulation optimization examples. So the example that I'm showing you from the agriculture with recourse decision variables are one of these stochastic optimization problems. It's very easy and it's very useful. So let's look into it. This workbook has 4 different worksheets. If time allows, I will show you all 4 of them, but if not, we're just going to focus on deterministic model and stochastic model. After that, this model shows you how to fit a distribution, how to deploy the distribution and save it on Raison server, and how you can actually import your saved distribution and use them in other models. This worksheet contains a linear model that determines how much a farmer should plant, sell, or purchase in order to maximize his profit. And it doesn't include any uncertainty. So the farmer has 500 acres available to plant grains such as to plant either grain, corn, or sugar beets, and to sell them according to these different prices. Okay, and we have the sugar beets above 6,000 tons are 36 per dollar, below and then above 6,000 are cheaper. Okay, due to agricultural restrictions, regulations. Okay, remember those constraints. Additionally, these are his requirements for his own cattle. He needs 200 tons of wheat, 240 tons of corn to feed his own cattle. And these can either be raised on the farm or brought from market. Okay, and the prices are present. So production cost, purchase amount, okay, and the minimum requirement he has for his own cattle, 200 and 240. So planning cost we know it's presented there. And the average yield of 3 crops, we know them. 2.5 for grain, 3 for corn, and sugar beets is 20 per acre. Okay, this is very important. This is where the uncertainty will come in the next example, the yield of crops. Problem description. The farmer must decide on amount of each crop to plant, sell, and purchase before the amount of rainfall in the season is known. The amount of rainfall, of course, is uncertain, right? But in this part, we are not going to worry about it. Okay, we are not going to incorporate the uncertainty in this version of model. So variables are amount of acres, okay, to devote to grain, corn, and sugar beets. And this is the first set of variables. And then the variables in D30 to I30 are amount of grain, corn, and sugar beets to purchase and sell. So I separated them. This is how much he has to invest in using his own land, okay, produce, and then this is how much he can sell and actually purchase. All of the decisions must be made here and now. Okay. In the next example, you will see that in the stochastic model, we are going to look at another approach, which is wait and see approach, okay, in decision making. So variable bound. So let's click on Analytic Solver and quickly review this together. Of course, variables must be non-negative. Remember, we split the amount of sugar beets to sell because of the regulation, and we have an upper bound of 6,000 for after, because this is the sugar beets sold under 6,000. So we have 2 separate variables. Constraints have 4 different types of constraints, ensuring that land use for growing crops or raising livestock does not go exceed 500 acres. That's our total available land. So this is D33 equals to D32. So what is D33? Of course, sum of total variables for first group of variables in row 27, total acre. Then we have E33 should be greater than D18. This is for grain balance. We want to make sure that we have enough grain to feed the livestock, and then same for the corn and sugar beet. And then the G33 greater than 0 ensures that the amount of sugar beet sold does not exceed the amount of sugar beet purchased and grown. And this is just a formula calculating the balance. Amount of sugar beet sold, F27, F16 based on acre. Remember, there's a yield, right? So we are multiplying the amount of acre used for sugar beets multiplied by the yield per acre for sugar beet. Objective function is to maximize total profit. So this is total profit. We're just calculating total production cost. Let's go ahead and solve this optimization and get the result. Click on optimize. Continue. This is a LP convex, linear programming convex model. Then we get the results. So here's the plan. We are using actually the whole 500 acre. Okay. And this is the plan to sell. The sugar beet sold is 6,000 based on the 300. We don't need to purchase anything. And everything is less than 6,000 for sugar beet. And we are not selling any corn. We just use it in-house. I hope you enjoyed this model. I'm very excited to share this with you. We are going to introduce uncertainty to make this model more realistic. The yields of tree crops are uncertain and are highly correlated with the amount of rainfall. And this is real, right? We don't know how much rain is going to come. So the yields of wheat, corn, and sugar beets are assumed to be uniformly distributed between these numbers. So here we have uncertain distribution. Instead of fixed numbers for the yield, here we have distributions because we don't know, right? But we assume, according maybe to historical data, what is the rainfall in that area, that the yield for grain can be anything between 2 to 3. 2 is the lower bound and 3 is the upper bound. I hope you are very familiar with our Monte Carlo simulation, how to define a probability distribution. Here we are using a probability distribution to model a source of uncertainty, okay? Same way for corn, we are using a uniform distribution from 2.4 to 3.6. And for sugar beets, we are using a uniform distribution anywhere from 16 yield per acre, 16 tons of sugar beets per acre, all the way to, in a very good rainy season, to 24 tons of sugar beets per acre, okay? So these are our source of uncertainty. Correlation matrix, you can see everything is 1, so they're all perfectly correlated. Of course, this is assumption. You can adjust this based on your application. How much land should the farmer devote to each crop? Okay, so as in the deterministic model, the farmer must decide on the amount of each crop to plant before the amount of rainfall in the season is known. Think about it as like a 2-stage. Currently, what does the farmer need to do immediately? He needs to use the land, right? That has to be decided right now, okay? We don't know the rainfall, but we can make that decision how much crop to plant. But it has more complexity than this. The decisions on the sale and purchase of each crop can be decided once the yield of these 3 crops are known. So we are going to think about it as a 2-stage kind of model. So the wait and see approach. Before going further to this, let me give you just a brief introduction into stochastic optimization, and then we come back and solve this model and learn more about how to use Analytic Solver for recurse decision variable. An optimization problem that includes uncertainty is usually called a stochastic optimization or a stochastic programming problem. We classify these problems into these following groups, okay, the following categories. The solution methods available in Analytic Solver for each category are written on the right side of slide. There are 2 groups, 1-stage models, okay? These are all 1-stage models. And then we have two-stage models. Today, we are going to look at a two-stage linear programming, and we are going to use stochastic programming methods to solve this problem, okay? And these are all covered in Analytic Solver. The presence of recourse decisions in the problem implies that at least some or all of the uncertainty will be resolved over the horizon of interest. So it's the condition for using the recourse decision variables or recourse constraints. Hence, we call the problem two-stage, where the normal decisions are made at the first stage before the uncertainties are resolved, and the recourse decisions are made at the second stage after the uncertainties are resolved. So first before the uncertainties are resolved, and the second group or the recourse decisions are made at the second stage. So solver must find first the single values for normal variables, and it will find multiple values for your recourse variables for each realization of the uncertainty. So for example, if you set the number of trials for your simulation 1000, it will actually return 1000 possibilities for your recourse variables for each realization of uncertainty that satisfy the constraints and still optimize the objective. Again, since the problem is linear, we can either use stochastic programming or robust optimization methods. And with these methods, we can solve much larger models, hundreds of times faster than simulation optimization. But sometimes we have to use simulation optimization, for example, when it's a nonlinear one-stage model. This was just the definition of this type of model with recourse decision variables, the two-stage linear programming method, and then some of the conditions that are hold. So uncertain variables are independent of decision variables, but problem includes normal decisions and recourse decisions, and problem may not include chance constraints. So this is the definition of when we can use recourse decision variables, okay? Now, let's go back to the model. So we have uniform distributions to represent source of uncertain variables, which are yields of tree crops, and that are highly correlated with the amount of rainfall. So the farmer must decide on amount of each crop to plant before the amount of rainfall is known in the season. After the rainfall, the yield of these three crops are known, and the farmer can make final decisions on the sales and purchase of each crop, okay? So we are going to use recourse variables for D32 to I32. So let's review the model together. So you can see that we have two sets of variables, normal variables and recourse variables. So normal variables are D29 to F29. This is how much to plant, and you have to use the 500 acre we have. And if you go to decisions, you can see we have normal decision variables and recourse decision variables. So that's how you define a decision variable as recourse. You define them as decision variable as normal as recourse, right, in the beginning. D32 to I32, these are amount of grain, crop, and sugar beets to purchase and sell. They are defined as recourse variables. So we have two groups of decision variables, normal decisions on planting and recourse decisions on sell and purchase to decide later. Our objective function. So we have to maximize our total profit. But remember that we will have 1000 different objective function values, one for each of the 1000 trials. Again, remember the default trial for simulation is 1000. You can always go to options and you can see that the default can be changed your trials per simulation. This is one of the ways you can change number of trials. So you can have 10,000, but in this example, we just stick with 1000. For each of the trial, we will have 1000 different objective values. However, solver requires the objective to be generalized into one function. An easy way to do this is to, for example, use mean or expected value of objective function. So this is the PSI mean of the 41 total profit. So we are going to maximize that. Of course, the other ways, if you go to objective and maximization, you can always see that you have expected objective function. You have always maybe so far worked with normal objectives, but currently now you can go ahead and use expected, okay, expected value of total profit or chance. This is something we'll cover in the future. So the expected is what we're doing here, but basically it's Sima mean. How you do that? It's basically under this result, and then statistics is the mean, okay? So basically choose that, and then you have to point to a function, Simin of that, and then place it in an empty cell. Okay, I'm just gonna skip. Any questions? So that's what you need to do, because for each of these uncertain variables, distributions, we will have 1,000 trials. So we have 1,000 different objective function values, but we want to maximize the profit across all of those realization of uncertainties. So we are going to use expected total profit. So now let's click on optimize and see what happens. So click on optimize. Important part, Analytic Solver automatically transforms this model with uncertainty into its stochastic programming deterministic equivalent. Let's click on next step. And here are the optimal results. So total profit, expected total profit, stage 1 variables, and some values for stage 2 variables, which I explained. So normal variables, which are stage 1 variables, these have optimal values. These are optimal values, okay? The recourse decision variables are not a single value. This is actually an array of array of variables, okay? An array of solution values for each of realization of uncertainties in the model. So to see all of these values, I'm going to click on Tools tab on the task pane. Follow, please. So Tools tab on task pane. I'm going to cycle through the 1,000 trials of simulation, and you will see different values for stage 2 variables, while stage 1 variables are optimized and they never change. So let's look at that together. Number 2, trial 3, trial 4. Okay, let's look again. Trial, for example, 5. And you can see stage 2 variables are changing, total profit is changing, but total expected profit is optimized value, and stage 1 variables are optimized value, so they are not changing, okay? So yields of wheat, corn, and sugar beets are uncertain. We model them with uniform distribution. Default trial was 1,000, so you can think of uncertainties as 1,000 different values. So now, when time passes, say 6 months later, and the uncertainty has become known, the amount of rainfall is known, hence we have actual values for total yield for each crop, okay? Then the farmer or you can replace the uncertain variables with those known numbers and do a simple solve for recourse variables. This is actually available. So you might have seen this before. If you go to optimize, there's a drop down, and you can see that there's an option for solve for recourse variables, okay? So let's assume it is now 6 months later. The farmer has planted the crops according to these optimal numbers to maximize total expected profit, okay? And 6 months has passed, and he knows exactly the actual measure yields, okay? So now the source of uncertainty is not present anymore. Instead of these uncertain variables, we actually know actual values, okay? But remember, stage 1 variables, we are not going to change because actually we dealt with this 6 months ago, right? So we don't have any uncertainty anymore. We only have the recourse variables. Now they become regular decision variables. So for your convenience, you don't need to do anything. You just have to go to optimize and solve for recourse variables, but there is one step. You have to take care of the yields, okay? One easy way to replace the yields with constant values without actually removing or destroying the uniform distribution. I want to show you a trick here, okay? There's a control parameter. So let's click on, for example, grain. And on the control parameters, there's an option called log, okay? So let's assume a number that the yield for this grain was 2.5. Just going to keep the middle number and click on save. Now this distribution will be locked and only value would be 2.5. Okay, same thing I'm going to repeat for corn. What are the numbers? 2.4 and 3.6. Let's go with 3. Lock at 3. Save. Basically, these are actual values, right? The farmer has seen the rain. We know how much yield we have. And then let's change the log for sugar beets. Let's change it to 20, for example, okay? Lock it at 20. Save. Once I do that, Of course, if the farm is really lucky, the measured outcome could be exactly one of the values that was simulated, then he can just pick the answers. But in case that they are different, okay, let's go ahead and click on optimize, solve for recursive variable. So now we are going to solve for recursive variable. Let me move it up so you can actually see optimize, solve for recursive variables. And here are the results. You can see these are our values, 2.5, 3, and 20. And here are the optimal values for the grain sold and purchase. Okay. And then the total profit for that. So you can see in the task pane, first stage was the stochastic transformation, and the second stage we solved for the recursive variable and got the results. This was just an introduction to stochastic optimization. There's much more that you can do using the power of Analytic Solver. Click on examples, work with the stochastic optimization applications with different approaches using chance constraints and those one-stage problems. And of course, this would be a good topic for future webinar. Just let us know in the feedback and we're happy to work on that for you. Just focus on stochastic optimization maybe for one webinar. If you're interested, you can look at other workbooks here. So if you want to look at all those trial values for simulation, and each time you want to run the model, you want to make sure you get the same results, go to options. Sorry, go to options, and under simulation seeds, you can set a seed for each individual uncertain variable, but if you want to set a global seed, then you set it here. Okay, so every time you run the simulation, you get the same result. So if you want to see all the trial values for all those 3 models, you can actually use the PSI data. So if you want, I want to show you how you can run one simulation and you get all the values. So now they are fixed, right? This is interesting because I locked them at 2.5, 3, and 20. So basically you're getting all the same results for the 1000 trials, but this is supposed to be different ones, right? Not locked. So if you remove the lock, run the simulation, this shows you how you can fit a distribution to this data, how you can deploy these distributions. Click and deploy cloud service, promote this fitted distribution. Here we're showing you how to use network distributions. Click on probability model and actually promote them to have them on Analytic Solver Raison server. Okay, and then in the next example, it shows you how if you go to distributions, there's an option here, import, that you can import the distributions from Raison server and use them in the model, your own fitted distributions. Okay, so there's much more here. Let's go to our slides for a summary of what we for a quick recap. So today we explored a few of Solver capabilities that are available to you. Analytic Solver allows you to define and solve deterministic optimization problems, stochastic optimization, and Monte Carlo simulation, risk analysis, and much more. Okay, with power of Analytic Solver plus Raison, sharing your model results with your team member become really easy. You can go beyond Excel by using a cloud service. And today we also talked about VBA, how you can model and automate your multi-stage optimization models. Remember to watch our previous webinar on learning to work with promoting models and be able to run them on Raison's cloud service and make them available to other people and create your own application. Let's go back to contact information. I want to again thank you for joining us today to learn more about Analytic Solver and all the tools it offers to you. Here are some contact information of our team members. Today with us we had Allison. I'm going to unmute Allison. Allison, if you want to introduce yourself.
Hi, thank you everybody for joining. We really appreciate it. Account manager at Frontline. So if you have any questions regarding your current licenses, any additional information on upgrades or account inquiries, feel free to email me at allison@solver.com.
Awesome. Thank you, Allison. And you can always, sure, go ahead.
Sorry, I'm sending the recording in the newsletter as well as the PowerPoint.
Yes, sure, we'll do that. And if you have any questions, if you want the slides or you want the example model, email me at consulting@solver.com. We trust this webinar refresh your perspective about using stochastic optimization using VBA and equip you with some new tools. And thank you very much. Have a wonderful rest of the day. If there are any questions, we will be here for a few minutes.